Probability questions involving taking one thing and saying, what's the probability that one thing is, older than 7 years old, or that the snail traveled more than 20 meters, make a Z-score and all that kind of crap, right? But what do we normally work with in statistics? What's the very first thing we do when we're going to do data analysis? What do you do in statistics when you want to figure something out about a population? Huh? Observe
Take
what?
Observations. Or
From
surveys.
what? Survey, so you collect a sample, yes. So you take a sample. You guys. So, for example, if I wanted to test out a new drug and I wanted to show it was more effective, right? One of my favorite examples is you create a statistics-specific pain reliever medication that you can take for the headache you get trying to figure out what the hell Jeff wants from you, right? And I claim that it acts quicker for any individual person. Even if the medicine acted quicker than the other medication that exists now, each person's going to react differently to that medication, right? So a single person having a quicker pain relief time than the average isn't good enough evidence that my pain reliever is better. Are you guys with? What would be good evidence is if an entire sample, if their average was less than enough than the normal average for the current medication, that's evidence. Then I can go on TV and say, it's been clinically shown. And, when they say clinically proven, they mean there's been control group, and there's been, the group you give the medication to, and then there's a group that gets the sugar pill, right? And all that kind of crap. And you do the statistical analysis, but you took a sample, and you showed that sample's average was very different, in this case, hopefully, below the average for the medication that exists now. How are you guys doing? Yes, maybe? So, we had to start somewhere to make it easy to understand Z-score. So we started with taking one person from what was known to be a normal distribution. How many things in life are actually normally distributed? Not a lot. Maybe more than you think, but still not a lot. Not a lot of things. So, the really cool thing then is we don't normally just take one thing. I want to test a group of people. I want to look at a group of things. I need to take more and more data to collect evidence. I need a method that takes into account that I'm talking about a sample of things, not just one thing. And in so doing, oh yeah, I just said that for you. In so doing, we actually create a distribution that is approximately normal if my sample is big enough. Oh shit, so let's remember what the hell we did last time. Does anybody remember alternate reality Florida from last time, right? So we had just a real quick ages, in this alternate reality Florida. So if you weren't here, maybe you want to look at the video. So there's a mean, and this is if I took one person at a time and plotted their age. So I said, how old are you? 1 year. Okay, bam. How old are you? 87, bam. Whatever. So now what we're going to do is if I took, let's just cut to the chase. If I took like 40 people at a time, randomly select 40 people from this alternate universe Florida, the picture's not going to look like this if I start, no, this is the key. This is key. This is what people forget. If I just go take 40 people, will that sample be normally distributed? I have no idea. If I take every group of 40 people and I plot all those means, then the result will be normal enough. Because all you need is, I don't know if you guys remember from last time, all you need is sample size bigger than 30. Why? And I kind of built us in this direction last time. Do you guys semi-remember? So it's like 2 days ago, so it's a long time ago. The most likely thing is a mixture of people, so that's why this is such a huge place. That mean becomes the most likely thing, which is why it's called the expected value. any group of 40 people I pick, what's my best guess for the average age? Whatever the shit the actual average is. Because that's what most of the groups of size 40 should have as an average. I love you guys. How are you doing? You doing all right? I know. All right. When you're taking a class, and especially with me, there's the whole, why does something work? And then there's the part where this is what you're going to actually have to do. Right now, we are still in the why does something work area. We haven't gotten to the point of, well, you're not going to have to construct parallel universes, right? That would be awesome if you did. That could be extra credit. Okay. So, one immediate consequence from this is what I just said. And how did we observe this? We actually used simulations on all kinds of populations. And we noticed that around 30, almost no matter what it starts looking like, it becomes normal after 30. After you get a sample size of 30. So it starts off looking really disgusting. Why isn't this like really disgusting? Because it's at least symmetric, right? Do you guys see that? So the nicer it starts off, maybe it becomes approximately normal at 15 instead of 30. But if I made something really disgusting, just crazy crap, then I'd have to get up to at least, greater than 30 before I can say, oh, it's going to be approximately normal. All right, so one thing is, and this is a central limit theorem. If n is greater than 30, the sample means will be approximately normally distributed. That's basically what this picture is capturing. Okay, that's one thing. Second thing to notice up here, which I'm really glad, well, I don't know if it's just because you guys don't like to talk much, but recently I've had a lot of trouble getting people to understand that, for example, there's an average age in this room right now. I can ask each person their age and then average those. If I ask 2 people, take an average, the next 2 people take an average, the next 2 people take an average, and then average those averages, of course it's going to come out the same as the average of everybody. Does that make sense? Or maybe it's just you don't really listen to what I'm saying, and that's why you're like, sounds good. Because in the past, I've had people go, what the shit? Why is that? Well, it's the same people. Just because I'm taking 2 of you at a time doesn't suddenly make everybody older. Let's take 2. Oh, I feel weird. Oh, shit. Right. Maybe. Okay. So if I take a sample of greater than 30, then I know that that sample lives in a normal distribution. So where is the sample that I actually would go take? Maybe it's right there. Maybe it's right there. Where is it most likely? Somewhere in here, right? So for example, we're going in the direction of, I claim that my drug works this fast. And I give it to a sample of people, and the sample shows up there. Now really think about this. I claim that my drug works this fast, in this many minutes. Let's say 15 minutes. And I give it to a random group of 40 people, and their average shows up right there. What do you think about my claim? I claim it's 15. I claim on average my drug is going to get you to feel better in 15 minutes. I give it to a sample of 40 people. Their average shows up there. How likely is it that I'm right? If I'm right, where should the sample show up? Around here. That's where most of them would show up, right? So is it impossible for me to be right and that sample to show up there? No, because there are going to be some up there. Is it likely that I'm right and the sample shows up there? No. So what's more likely? I'm wrong. I'm full of shit. Does that
by itself, that's going to be the entire thing behind chapter 9, is what I just said. Chapter 9 is going to be everybody's most hated chapter. I'm sorry to have to say that. I normally don't make blanket statements like that, but it just is. But really, that is it behind chapter 9. If I think it's here and I get a sample so far away, that's probably wrong. That's chapter 9 in a nutshell. Just try to remember that when we get to chapter 9. I'll remind you. And then you'll have this big-ass problem. You're like, you're silly. Now, the third thing that's not as obvious, the third thing, we can tell this is true on a surface level. What happened to the standard deviation? It got a lot smaller, because here, nobody's close to the mean. Here, almost everybody's close to the mean. And standard deviation is a measurement of how far away your data points get from the mean. So the standard deviation got a lot smaller, and this is where I introduce, well, this is where statistics, not me, introduces this symbol. And actually, I just used it here, too. That's a subscript. That's not divided by. So this is the standard deviation for the sample means. This is how spread out sample means are. This symbol is how spread out individuals are. I like it. So if I'm doing a question about what's the probability that one person is older than 70, we've done that problem before, right? I have to know it's normal, so I couldn't do it for this, but we know that kind of problem. I make a Z-score, I can look it up, I can get the answer. If I ask, what's the probability that a group of 40 people is older than whatever, I can't use this. I have to use this. And then your question, and why do I have to use this? Because that's the spread for groups. And what am I working with in that problem? A group. Not an individual, I'm working with a group. So then a really good question is, what the shit is that, Jeff? You got a little symbol written down. That's nice for you. They're not going to tell you what this is. Here's what this becomes. The standard deviation for the sample means becomes the standard deviation for individuals divided by the square root of n. Now let's at least make sense of parts of this. If I take a larger and larger and larger sample, like if I take 40 people, that group should be close to the mean. If I take a sample of 400 people, that's going to look more like, I mean, it should be really hard for 400. Imagine taking 40 people. And what's the average? Well, probably their average height's more than 6. Well, that's pretty unlikely, but still. If I take 400 randomly selected people, what's probably their average height is more than 6 feet tall? Ain't gonna happen. Why? Because a group of 400 should be really close to whatever the actual average is. That's 400 frickin' people. Maybe. And that's why taking a sample size of like 1,000, like Gallup does from the United States, you think there's 300 whatever million people. Why would 1,000 people? Because once you get 1,000 randomly selected people, what you see should be close to reality. Give or take. And that's going to be chapter 8, the give or take. Okay, so right here, the standard deviation becomes the old one. So this is what I call the new standard deviation. The new standard deviation is the old one divided by the square root of n. Okay, so let's do this. Let me give you this. So look at the very colorful side. For me, very colorful means 2 colors. Oh, scheiße. People made us a 2-week spring break for some of the classes.
I know if I were one of you guys right now in this class, I'm really worried about what the hell I'm going to have to do. This is not what you're going to have to do. This is still explanation of concept. It's very satisfying. All right, so everybody get the initial part of this, right? Everybody's looking at this. Read the very first sentence on there. Okay, so we have 4 numbers in a hat, right? And I'm going to pick one out. So obviously the probability that I pick any number is 1 out of 4. So I kind of constructed a histogram that we can look at really closely there. So I mean, this is kind of silly, right? That would be a uniform distribution. Everything has an equal probability. So would you say that's a nice distribution? Is that a clean, nice distribution? Yes. Like this is not a nice one, but it's still symmetric. So if I had one like blah, 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 that's gross. Stay with me now, come on. That 30 requirement is for any distribution. So what's really interesting here is I'm going to end up taking 2 numbers out of this hat instead of 1. So I'm going to take a sample of 2. So what could I pick out? And I'm doing it with replacements so all the probabilities don't change and get all weird. So if I take out a 1, I drop it back in, I could take out the 1 again, right? Or if I take out a 1, I could take out the 2 next. So I've listed all the possible samples. So this was the theory. This was me saying, what if I did take 40 people? And here's an example of, well, here's it in your face. Here's all the samples I could possibly take. All right, I like it. So is everybody cool with what this here represents? So I could take 1, 1. The sample mean would be 1. I could take 1 and then a 2, and then the sample mean would be 1.5. What's the average of all these? Well, I got it right there for you, right? 2.5. And what's the most likely sample mean to get? 2.5. I like it. Now this is, I made it nice 1, 2, 3, 4, nice and symmetric, but it is a small sample size anyway. Okay, so everybody understand this here with all the yellow. So now, when I graphed this and I made the table, my values, my actual data points were just 1, 2, 3, 4. Now my data points are 1, a couple of 1.5s, 3 2s, 4 2.5. So now my sample means are going to be what I plot. So when I plot those, I kind of collect them all together here. There were 2 of these, there were 3 of these, there were 4 of these, right? And when I plot those, does that look normal? Does it look more normal than it did? Here's what it looked like. And now there's what it looks like. So if I took 3, and you can see why I didn't, because if I took samples of size 3, that would take up the whole paper. This would look even more normal. It would look even more bell-shaped. So why did it only take 2, and I'm up here saying 30? Because, again, this started off stupid nice. It started off really nice. It's symmetric. It's uniform. It's beautiful already. So it didn't need a big sample to become more normal. I love you guys so much. Now, give me an example. Somebody give me one sample that I took. What's one sample that I took? Just give me any sample that I took. 2, 1. I love it. So there's the sample 2, 1. Where's that on the picture? At the 1.5, right? It's one of these here. Are you guys with me? So any sample I pick isn't normal. The sample 2, 1 is not normally distributed. That's insane. It lives in a normal distribution.
Now what really kicks ass, right? And I can see in your faces you're semi with me, but what really kicks ass, up here, this is silly. I could just do one var stats and get the freaking standard deviation. You guys with me? I could do the same thing here, to be honest. I don't have to do all this XP of X bullshit, because I could just put all of these in the list 1 and do one var stats. And what do I get? I get a mean of 2.5, the same as what it was, and I get a standard deviation of 0.791, which is the old one divided by the square root of 2, which is what n is. That does equal what the standard deviation now is. So if I took samples of size 3, I could predict what the standard deviation is going to be. I could just take 1.118 divided by square root of freaking 3, right? I don't have to do all this shit. I could just figure out what it's going to be. I like it. So we're getting closer to what you're actually going to have to do. You're not going to have to actually do all this. So let's do a couple examples, and then I'm going to unleash you on the reverse side of this. Let's finally do some concrete examples. And you guys missed all that on the overhead, but oh well. So here's what's going to happen. We know, what do you got, Jeff? The average travel distance per day for a snail is 17 feet. I don't know. This is obviously heavily researched. You were like, there's that snail guy watching that snail. What the hell's he doing? Getting a problem together for my class. 17 feet with a standard deviation of what, Jeff? What sounds good? Well, let's say some snails are really, let's say 5.29 feet. I like it. Now let me see if you guys know. Let's see. If I ask you right now, what's the probability that a snail goes more than 20 feet? Let me just save some of you from yourselves. Why can't I answer that? Why can't I?
Oh, because the average distance is 17.
That's all right. So, what would I have to do? What kind of problem would this be? What would you guys do first? You would draw the picture. What goes in the middle? Now, right there, what have I done wrong?
Not normal.
We don't know if it's normal or not. So I can make a z-score for anything if I know the mean and standard deviation. I can make a z-score all day freaking long, but what's the only time I can look up the probability is if I know that it's normal. Do I know this is normal? No. So I couldn't even do that problem. But if I tell you we take a sample of 47 of these snails, what's the probability that their mean is more than 20 feet? Why can I do that problem all of a sudden? What is it that we have to look for in these problems? It doesn't tell me it's normal. I can't do that problem. All of a sudden I could do that problem. What the shit? Sample size is bigger than 30. So then I know that whatever sample I pick will live in a normal distribution. I know that the means will be normally distributed. Enough. N equals 47. Bigger than 30. Now before I go calculating anything, what do I need to get? So what's it going to look like? If I draw this picture, now I know it's normal. What's going to go in the middle? What goes in the middle? 17. Right, that's the mean. 17 goes right in the middle. Then I put my 20, and that shade more than. And then you go to make a z-score, but what do you not have yet to calculate your z-score for this problem? I don't have the right something. So, what does this work for? What is that for? That's the what of what? What's the standard deviation tell you?
Distance from the mean.
Yes, so the spread for individual snails. How far an individual snail's travel is away from the average. What am I talking about right here? A group of freaking 47 snails. So do I have the right standard deviation yet? No. All right. So guys, there's a lot of, and you know this because you've lived through it, a lot of Jeff talking, gesticulating, using two colors, which is two more than normal for him, to explain this idea. And then at the end of all that shit, what actually happens in a problem is before you make a z-score, you don't do z equals 20 minus 17 divided by 5.29. You figure out, well, what's the new freaking standard deviation? The old one divided by what? Square root of n 47. So help me out, what is that? Somebody help your old gesticulating weird teacher. That word gesticulate is just a weird one. I think it's about 1.19, 1.18, 1.17. I could be really wrong. I'm trying to do that in my head.
0.777.
Where did I come up with the extra one? Damn. 1 point who?
No, 0.771. 0.77.
0 point. Oh my god, I'm really bad today. 7716. Why did I think that? Oh god, Jeff. All right, I know what I do. That's what happens when you do things in your head. So I can make it 0.772, right? 7716 is fine also. So that's what I use. That's the concrete thing that changes. So what's really the most important thing out of all the stuff I've talked about is this standard deviation that they give me is for individuals. So hopefully it should make a ton of sense. If they ask me about a group of something, I can't use that shit. That's for the spread for individual snails. I need to figure out the spread for a group of 47 snails. It's not going to be the same. That's what all the alternate universe shit was to show you. It ain't the same. It gets smaller. Can't use that. It's not a question about one snail. It's a question about 40. Shit, you got to change it. Now I throw that thing in to make a z-score. I don't use that. Got to use a new one. So that's the one thing that changes in the whole process. It's just change the standard deviation. Isn't that crazy? Plus, there's a bigger thing here. I couldn't even do this problem. So what's nice? What normally happens is I take a sample, and theoretically, if the sample's big enough, I end up with something that's approximately normal. I can use my sheet of frickin' answers, the z-score chart. Love that shit. What we normally do actually lends itself to making things easier. That's awesome. I don't know. What do you get here? I'm not even going to try. I'm not going to trust myself today, apparently. I'm still trying now, if nobody says anything.
3.886.
So 3.89?
Yes.
I like it. Somebody remember why that's a weird number if you look at your z-score chart?
Oh, yeah.
Z-score only goes up to 3.5. So according to the book, and I told you this is okay to say, this is 0.9999. Aw, you gotta retire, dude. And this would be what? So that would be the answer, 0.01% chance. I would say about a 0% chance because it's well off the chart. So I'll take either one of these because that's what the chart says, and I'm telling you to use a chart, so it would be evil for me to not take this. But this is more conceptually correct. So basically, if this is true, the probability that a group of 47 snails travels more than 20 feet on average is almost impossible. This is going to be a really weird example for this, but I don't care. So if I am somewhere and I am just into snails, and I notice that this group of 47 snails traveled more than 20 feet on average, something weird is happening, because that should be basically impossible. That is evidence that these snails are eating some super snail food or something. The water's great, or I don't know, the surface is easier to travel on. I don't know. Something weird's happening. Maybe. Okay, so why was it I couldn't do this again? Because this is picking one snail. It's probably that one snail goes more than 20 feet. I couldn't do that because it doesn't say that it is normal. I like it. So turn this over. There's going to be a part A that's picking one person, in this case one woman, to look at her bone density. And then there's going to be a part B where you take a sample of women, so that's when the new shit kicks in. So you can do both now. Why? Because what's it say at the top of number 1? The second sentence. There you go. Sweet. So, do that. Do those problems back there. Does everybody have one of those sheets? I've already lost somebody. And everybody's got a Z-score chart, right?